We've come a long way in Chapter 4. Think about all you've accomplished. You've learned Newton's 3 laws. You've also learned how to apply Newton's second law in a very simplistic format where sigma F equals ma. And from that, you were also able to work through how to convert weight into mass and mass into weight by applying acceleration due to gravity. Then we took Newton's second law and we expanded it, and we, instead of scooping all of the forces together into sigma F, like we did with the very first set of problems, now we decided, okay, we're going to break these down and see what the individual forces are doing and how they're affecting motion. And so then we used Newton's second law to find acceleration, and from acceleration then we could apply it using kinematic equations to find a piece of motion. Or we work backwards, where we found a piece of motion, were given a piece of motion, used it to find acceleration, and from acceleration then we could find an individual force acting on the system. One last piece to this puzzle that we still have yet to do, and that's to have a conversation about friction. You remember that friction comes up when we're identifying the forces in a free body diagram. The very fourth question, let's go through all of them. The first question is there weight? Yes, always and always vertical. Second question, is there tension on a rope or wire or a push or a pull? The third question is there force of contact, which happens when an object is resting, rolling, or sliding on a rigid surface. It is never going to be there when the object is experiencing purely vertical motion. That the last question is, was there any conversation about friction? And up to this point it's been no, because we hadn't yet learned about friction. So we're going to start that now. We're on Roman numeral 4 in our notes. And Roman numeral 4 is friction, and something that I want to say about it right up front is that it always opposes, always hinders motion, always opposes motion. If it always opposes, then what is always going to be true about friction? Because of that, it's always going to be negative. There'll never be a question about, is this force positive or negative? When it's friction, it's always negative. There are two types of friction. The first type of friction is static friction. And what do you think of when you think of static friction? When you think of static, what do you think of? Hopefully it kind of draws you back to our second chapter, which was about statics. And in all of those cases, we had created equilibrium so that the object was at rest. So static friction acts on an object that's at rest, and it opposes the initiation of motion. And I'm not sure I'm going to have enough room for this. You do in your notes. Opposes the initiation of motion. So when something you would think normally would move, it's not going to move. I have a little drawing here. It's a demonstration that I give every year because I have this nice handy-dandy little podium, and I put my mug on the podium, and yet it does not slide, even though its weight should be pulling it down, because when I draw a free body diagram here, I'm going to make this my XY axis, because that's the direction it would move. This is my force of contact, which is going to be cosine of 90, which is 0, and this is my weight. And notice there's no other force right now in my free body diagram acting on it to keep the weight from pulling down, because again, force of contact in this case is going to be cosine of 90, which is 0. So there should be a sliding motion on my mug, but the mug sits perfectly still. And this is this is what I'm talking about then with static friction. It exists when an object does not slide on a surface, even though forces exert it to make it slide. So the force that was exerting on the mug was its weight to pull it down, so something had to be balancing it out to keep it from moving, otherwise there would be acceleration. If there's no acceleration, then you have balanced forces, so something had to balance my weight, and in this case it is static friction, the friction that opposed the initiation of motion. Now the factors of friction are, letter A, the roughness of the surface, And the other factor, and maybe you could predict these, but a lot of people say weight, and it kind of is, but not really. Instead of weight, it is the magnitude of force of contact. And I'm going to also put what you'll see it as most often, the normal force. Force of contact, or the normal force. So the equation for this, or the formula that we're going to use, is F sub S, and in this case S is standing for static friction, the force that keeps an object from moving, is equal to mu sub S. Mu is a Greek letter, and you'll see it also printed like this. So it looks like a U, but it has a tail on the front. Mu sub S, which is what is going to measure the roughness of the surfaces, times F sub C, the two factors. And let me explain then where mu sub S is called. And be very aware of this name, because you're going to see the word, I can't spell, coefficient. Let me finish writing it, then I'll explain. Coefficient of static friction. And you need to know about it that it is constant for a given set of surfaces. So tire on the road, that would be a constant that you would be able to look up and say, okay, the coefficient for static friction of a tire on a road is this number. It would be constant between skis and ice, but it would also be very specific with how wet the ice is as well. It's very, very specified, but it is constant for two given surfaces. So it's constant, and it is a ratio. And because it's a ratio, it is going to be unitless. I don't know if you remember me using this before. That little symbol means therefore. And because it's a ratio, it is unitless, which is kind of a good thing, because I start with force and I end with force. So I need a factor in there. I need the other thing that I'm multiplying it by not to have a unit, or I wouldn't end and start with force. So I was saying earlier, be familiar with this term, coefficient of static friction. You're going to see the word friction, and you're going to want to call that the force. If it has coefficient in front of it, it's talking about mu sub S. It's talking about one of the factors of friction. It is not itself the friction force. So be careful, because you'll see static friction, you'll see kinetic friction, and you're going to want to call that the force, but it is not. It is just a factor when the word coefficient is in there. All right, now the next thing I want to do is show you an example, and I'm going to use the next page for that. And the next page, we're going to do number 5, which is C4.6. Nope, that's not what I want. I'm sorry, I'm way off here. Let's do 4.11 instead. And let me read that for you. I'm sorry, I've got several papers sitting here, and I just need to get myself together. 4.11. A 150-pound box sits on a floor. The coefficient of static friction between the block and the floor is 0.4. Notice there's not a unit for it, is 0.4. What magnitude of horizontal pushing force, P, is needed to make the box slide? So the way I'm going to set this up is I can do it two ways. Number 4. Oops. Is C4.11. And one of the ways is that I want when static friction is at its highest, it's right before it's going to allow acceleration to happen. So I could set it up this way, where sigma F sub x, and I'll do my drawing, so I'm actually following the rules. Here's my drawing, and something is pushing on it. So we're going to call that the force of the push. We'll take it all the way through to the side. So force of the push. And I have weight going down. I have force of contact going up. And then I have my static friction going in the opposite direction, opposing the motion. Now, right up until it starts moving, I want to find what is the force of static friction. So this is how we're going to do it. Sigma F sub x is equal to the two forces. I'll do all of them. F sub c sub x, which we know is 0, plus w sub x, which we know is 0 because they're both cosine of 90, minus F sub s sub x, and I know that it's minus because friction is always an opposing motion, plus the force of my push sub x is equal to ma sub x. But I also know that right now it's not moving, so a sub x is 0 because my friction is holding it in place. So what's going to happen then is, let's figure out my F sub s is, and we'll do that as its own equation on the side. So F sub s is equal to mu sub s F sub c. Mu sub s, they told us, was 0.4. And in this case, F sub c is going to be equal to weight because everything is horizontal. The push is horizontal, the motion is horizontal. So in this specific situation, F sub c is equal to weight. So I can just use the 140 pounds that I was given. So my static friction is going to be 60 pounds. So now I can put that into my equation. Sigma F sub x is equal to a negative 60 cosine of 0 plus p cosine of 0. Oops, I don't know why I wrote that lower. Plus p cosine of 0 is equal to 0 because we said a sub x is equal to 0. So negative, I'll just make it p, is equal to negative 60 when it is at equilibrium. The push then has to be anything greater than 60 pounds because this is what said it's at equilibrium. When the push is anything greater than 60 pounds, motion will occur. Now you'll have a question like that in your homework. If you told me P is equal to 60 pounds, I would mark that wrong because at 60 pounds there is no motion. I'm still at equilibrium because the two are equal, because the two are equal to each other. As long as my P is greater than 60 pounds, then I'm going to have motion that occurs. All right, so that's the application of this. Kind of an important thing here is the reminder that when everything is horizontal, force of contact is equal to weight. Notice that it called for the coefficient of static friction. That was not itself static friction. So I used mu sub s when I saw coefficient of static friction. All right, now let's try and see what this looks like in our setting where things are moving. And that's going to be capital letter B, kinetic friction. And just like you would guess, kinetic friction is going to oppose motion already occurring. Oops. Wow, this iPad just gives me so much fit sometimes. Opposes motion already occurring. And it's very much like it's very much like static friction in the way that you look at it. The two factors are going to be the roughness of the surfaces and the force of contact. So number one under this, the formula is going to be, instead of F sub S, I'm going to put F sub K is equal to mu sub K, which is going to be the coefficient of kinetic friction, times F sub C, and mu sub K is called the coefficient of kinetic friction. And again, it's a constant for two surfaces, and you'll either be given that or you'll have to find it because you're given everything else. But very often you're given what mu sub k is, coefficient of kinetic friction. And again, be careful when they give you coefficient, that means you only know a piece of the friction, not the friction itself. And let's go ahead and look at 4.12 then. Police examining the scene of an accident observed the skid marks 30 meters long left by a 1,200 kilogram car. The car skidded to a stop on a concrete highway having a coefficient of kinetic friction with the tires of 0.8. Estimate the car's speed at the beginning of the skid. And what's going to happen with this one then is this is going to be just like all of the ones that we've done in the past, only now I have that one more factor of friction, kinetic friction. So I have to ask myself, is this a right to left or a left to right problem? Because you're starting out looking for, because the end of what you're looking for, is speed, because that's the very last thing, then I know I'm landing on the D, the V, the T of the side of things. And so I'm going to be going from left to right. I'm going to use my sigma F, or Newton's law, process to find acceleration, and then acceleration to find the speed. So I'm going to apply Newton's second law. So I'm going to start by giving a drawing. I'm going to be very basic here. Here's my car. I'll give it a couple of wheels just so that it looks a little realistic. No, not really. And first thing, do my drawing. Next thing, put in the force diagram. So I'm going to ask myself what all is going on in this system. First of all, is there weight? Yes. And of course it's vertical. And the weight, they give you the mass of the car, which is 1,200. So this is going to be 1,200 times 9.81 for the weight. And that's actually going to be important. A lot of times we do that and we don't use it, but it's always a good habit to get into. And so the weight of the car is going to be 11,800. And, yeah, I did that right. And then the force of contact, that's going to be Newton's. Force of contact is going to be the same as weight because everything is horizontal in this. But let's do it one question at a time. I'm sorry, I'm getting ahead of myself. Is there weight? Yes, and we figured out what it is. Is there tension on a rope or wire, push or pull? Is there anything acting outside the car to move it forward? And the answer is no. Actually, the car is moving, and then when we jump into it, the car has slammed on their brakes and skidded to a stop. So what was it that changed the motion of the car? Not because something is pulling it, but because instead the friction created by the tires and by all the other pieces of moving parts going on in this, the brakes especially, is causing it to stop. So this is going to be my force of kinetic friction. And since I know that I'm going to have to deal with kinetic friction, I'm going to find the formula on the side right away. So F sub k is equal to mu sub k F sub c. They told me that mu sub k is 0.8 and that my F sub c is equal to weight in this case because it's traveling on a horizontal line and it is also being pulled back horizontally. There's no angle to the force. So it's going to be times 11,800, and it is approximately a negative 9,420. If you get different numbers than that, don't worry about it. I rounded this before I plugged it in there, so it may be a little bit different than the 9,420, but that's what we're going to work with. So my force of kinetic friction is 9,420, and it's going to be negative. So then my sigma F sub x is equal to, and of course here is my, let me throw that in there, here's my xy axis. Sigma F sub x is equal to W sub x, which I see is going to be the cosine of 90, so that's gone, plus F sub c sub x, which again I see is the cosine of 90, so that's going to be gone, minus F sub k sub x is equal to m a sub x. So I have a negative 9,420 cosine of 0, that's how I get rid of my x here, is equal to 1,200 a sub x. Do all the math with this, and you find that a sub x is equal to a negative 7.85 meters per second squared. And then the last question is estimate the car's speed at the beginning of the skid. So now I'm turning this into a kinematics problem. I know D is equal to 30 meters. I know that V is what I'm looking for. I'm sorry, V naught is what I'm looking for. What was the speed at the beginning of the skid? But I know V final is 0 because it has come to a stop. And my acceleration was a negative 7.85 meters per second squared. And what equation am I going to use for this? My old standby. 2AD is equal to V squared minus V naught squared. And that cancels out. So I have 2 times the negative 7.85 times 30 is equal to a negative 30 squared. I'm sorry, V naught. Oh, that's what I'm looking for, is equal to a negative and then V naught squared. Wow, I got confused on that. I do the math, and give me just a second here because I don't have this one in front of me. 2 times, by the way, I'm going to cancel these out right away because my negative's on both sides. I just multiply both sides by a -1 and I'm good. So it's 2 times 7.85 times 30 is equal to, so my V naught squared is 471. Feel free to check my math on this one. I may be making mistakes here just because I'm doing this as I'm talking to you, is equal to V naught squared. So to find V naught, I just have to take the square root of it, and I end up with 21.7 meters per second as my final, as my my initial velocity. I'm just going to do that one more time. 2 times 7.85, just to check my math, times 30 is equal to 471. Take the square root of it. Yep, that's right. All right, folks, that is how you do these problems. If you want to get started on these, you can. I'm not going to have them due until Friday because I'm going to show you a couple more of these problems when we meet again on Wednesday. But the problems that I'm going to have you do will be 38, and I'm just going to put this on the next page so you can see it. You're going to do 38 through 40, and you really may want to get started on these because these are going to take you a little while. 38 through 40. 43 through 49. And eventually 50 and 51, and you'll see that those are added to the bottom of the homework sheet that I gave you. All right, go ahead and get started on these. See how you do with them. These are really not a lot different, except for you're only adding one more step to the problem, but make sure that you're actually solving for f sub k before you get started on the problem. You want to have that number